Hello, peaceful traveler. Take a slow, deep breath and let yourself settle into this moment. You are here now, present in this cosmic space, safe in your protected haven, ready to experience the universe unfolding its natural rhythms. Tonight, you will travel alongside this massive star, experiencing its complete transformation from quiet, glowing life to spectacular cosmic metamorphosis. You will be here for every moment, present but protected, witnessing but never in danger. Only wonder, only the slow and beautiful unfolding of nature at its grandest scale. Your journey begins at the beginning, in the long, peaceful era of the star's life, when it burns steadily and calmly in the darkness of space. You are here to witness it all. You are floating, peacefully, comfortably, in the quiet vastness of space. There is no cold here, no danger, no urgency at all. You are wrapped in warmth and safety, drifting in the gentle darkness between the stars. Around you, points of light shimmer softly, distant suns scattered across the cosmic canvas like luminous seeds in an infinite garden. And there, ahead of you in the distance, one star shines with particular brilliance. It is massive, ancient, and beautiful. This is the star you have come to visit, the star whose transformation you will journey through tonight. You drift closer, approaching this enormous star. If you could place our sun beside it, our sun would seem like a small ember next to a bonfire. This star is perhaps 15 times more massive than the sun, a red supergiant, swollen and luminous, glowing with a deep amber light that seems to pulse gently with each passing moment. It has been shining this way for millions upon millions of years, far longer than human civilization has existed, far longer than humans themselves have walked upon the earth. And you are here now, in this moment, traveling alongside it. Inside this star, deep within its core where you cannot see but can imagine, a magnificent process has been unfolding for all these ages. Hydrogen atoms, the simplest and most abundant element in the universe, have been fusing together in the intense heat and pressure of the star's heart. When hydrogen atoms merge, they become helium, and in that transformation, they release energy, gentle, steady energy that flows outward from the core like warmth radiating from glowing embers. You can almost feel this warmth from your safe vantage point, like standing near a great hearth on a winter evening. This energy travels slowly, so slowly, making its way up through layer after layer of stellar material. It takes thousands of years for a single packet of light to journey from the core to the surface. Imagine that light, which we think of as instantaneous, taking millennia to escape the star's dense interior. The light you would see from this star's surface today began its journey when humans were still learning to make fire, still watching the stars with wonder from cave mouths and desert plains. And you are here now, watching this ancient light escape into space. The star's interior is structured like an onion, with different layers performing different tasks. At the very center lies the core, where the temperatures reach tens of millions of degrees and the pressure is so immense that atoms are crushed together, forced to merge. Moving outward from this burning heart, you would pass through shells where different types of fusion occur. Helium burning into carbon, carbon into oxygen, oxygen into heavier elements still. Each shell glows with its own particular light, its own particular warmth. You cannot see these layers directly, but you sense them, you feel the complexity of this living star. This process of helium burning happens through something called the triple alpha process, a delicate and beautiful dance where 3 helium nuclei, 3 alpha particles, find each other in the cosmic crowd and merge to form carbon. It is a bottleneck, a narrow passage through which the star must thread its existence. And thread it does, steadily, gracefully, creating the carbon that will one day form the basis of life on distant worlds. You are witnessing the creation of the very elements that make up your own body. For now, everything is balanced. The inward crush of gravity, trying to compress the star into nothingness, is perfectly matched by the outward pressure of heat and light generated by fusion. The star breathes in this equilibrium, expanding slightly, contracting slightly, in a rhythm as old as the cosmos itself. It is a dance of forces, a cosmic meditation, and it has continued for so long that it might seem it will continue forever. You float here, breathing in rhythm with the star's gentle pulse. But nothing in the universe lasts forever. Everything changes, everything transforms. And deep in the star's core, subtle changes are beginning to occur. Your journey is about to move into its next phase. You are still here, still floating peacefully near this ancient star, and now you begin to notice something. The star has been burning for so long, fusing lighter elements into heavier ones, that it has created something remarkable at its center. Iron. Iron is special among all the elements. It is the most stable nucleus in nature, the element that sits at the bottom of the energy well. Fusing elements lighter than iron releases energy, which is what keeps the star shining. But fusing iron requires energy. It consumes energy rather than releasing it. And so, as iron begins to accumulate in the star's core, the ancient engine that has powered this sun for millions of years begins to falter. You sense this shift, this subtle change in the star's rhythm. This happens slowly at first, so gradually that, as you watch from your comfortable vantage point in space, you see no change at all. The star still glows with its warm amber light. It still hangs in the darkness, majestic and serene. But inside, in the core where you cannot see but can feel, the iron is building up like ash in a fire that has burned too long. You are present for this transition, this turning point in the star's ancient life. In these late stages of its life, the star moves through its final burning phases with increasing urgency, though even this urgency is measured in cosmic time. Oxygen fusion occurs in the core, creating silicon and sulfur over the course of weeks, weeks that are mere heartbeats in the life of a star. The star's interior becomes even more layered now, with silicon burning in the inner shells while oxygen and carbon continue their fusion in layers further out. The onion has grown more complex, more beautiful in its stratification. You are traveling through time now, days and weeks passing in moments as you witness these changes. Then comes the silicon burning phase, the last act before the final transformation. Silicon nuclei fuse to create iron group elements in a process that takes only days. After millions of years of steady burning, the star is now consuming its fuel at an astonishing rate. Yet from the outside, where you float, it remains calm, glowing gently in the night. Only in its heart does the frantic pace of change reveal itself. You can sense the acceleration now, the quickening of the cosmic heartbeat. The temperature in the core climbs higher and higher, reaching 3 billion degrees Kelvin. At these incredible temperatures, something strange begins to happen. High-energy photons, particles of light, become so energetic that they start to break apart the iron nuclei that the star has worked so hard to create. This is called photodisintegration, a process where light itself tears atoms back into their component parts. The iron that represented the star's final burning stage is being undone, and in this undoing, energy is consumed rather than released. You are here as the star reaches its critical moment. The star is losing its battle now. The core can no longer generate the pressure needed to hold back gravity's embrace. The fusion energy that has supported the star for its entire life is quenching, falling silent like a fire smothered by its own ash. The temperature, despite being billions of degrees, is no longer high enough to sustain the reactions the star needs to survive. Silicon burning grinds to a halt, leaving incomplete iron group synthesis scattered through the core like the last sparks of a dying ember. You feel the change, the shift from stability to imbalance. And then, in a final bright flash that lasts only seconds, a silicon burning flash that accelerates the star's fate, the last fusion reactions sputter and cease. The core, which has supported trillions upon trillions of tons of stellar material above it for millions of years, can support it no longer. You are here for this critical moment, this threshold. The transformation is about to begin, and you will experience it all. What happens next occurs faster than thought, faster than anything you might imagine in your daily life. Yet you are here to experience it, and time seems to slow for you, so you can witness each phase of this cosmic transformation with calm understanding. You are safe, protected, but fully present for what comes next. The core, no longer supported by fusion energy, begins to collapse. But this is not a slow settling, not a gradual sinking. This is a catastrophic implosion, a falling inward so rapid that it defies easy comprehension. In less than a second, a fraction of a heartbeat, the core of the star, which is roughly the size of Earth, collapses down to a sphere only about 20 kilometers across. 20 kilometers! An object the size of a planet, compressed to the size of a small city in less time than it takes to blink. And you are here, witnessing this moment. But to you, floating safely in your observation point, you experience this differently. To you, it appears as a slow, majestic drawing inward, as if the star is taking a deep breath, pulling its essence down into its center. You watch as the star seems to dim slightly, seems to gather itself, preparing for something momentous. You feel the tension, the gathering of forces, but you remain calm, safe, an intimate witness to this cosmic event. Inside the collapsing core, matter is being crushed to densities beyond imagination. The electrons, which normally orbit atomic nuclei at comfortable distances, are being forced into the nuclei themselves. This creates a flood of neutrinos, tiny, ghostly particles that barely interact with matter at all. They are called neutrinos because they are neutral, carrying no electric charge, and they are so elusive that they can pass through the entire Earth without ever bumping into a single atom. And now, as you float here, trillions upon trillions of these ghost particles are streaming past you, through you, carrying away the star's energy. More than 10 to the power of 58 neutrinos are created. That's a 1 followed by 58 zeros. It is a number so large that if you tried to write it out, the zeros would stretch across this entire page. These neutrinos stream outward, passing through the star's outer layers as if they were made of nothing but empty space. They carry away 99% of the energy released in the collapse, racing out into the universe at nearly the speed of light. Some of them pass through you, harmless and invisible, as you float here bearing witness. The core continues to collapse, the material falling inward at speeds approaching 1/10 of the speed of light. That's 30,000 kilometers per second, fast enough to circle the Earth in less than 2 seconds. And still, to you, watching peacefully from your vantage point, it appears as a slow gathering, a beautiful concentration of light and matter toward a central point. Time has slowed for you, allowing you to savor each moment of this transformation. Then, suddenly, the collapse stops. The core has reached a density so extreme that the neutrons themselves, the particles in atomic nuclei, resist being compressed further. This is called neutron degeneracy pressure, and it is the same quantum mechanical force that holds up white dwarf stars. But this core is far denser than any white dwarf. The material has reached nuclear density, the same density as an atomic nucleus, except now it extends across 20 kilometers instead of across the microscopic width of a single atom. You are here as this incredible density is achieved, as the star's core becomes something entirely new. The infalling material bounces. Like a ball dropped onto a steel floor, the core rebounds from its compression, sending a shock wave racing outward into the still falling outer layers of the star. This bounce happens in milliseconds, releasing the main burst of neutrinos that flood out into space. If you had detectors sensitive enough, stationed here with you, you would register this neutrino pulse arriving at your position, carrying the news that the core has collapsed and bounced. You feel the moment, even if you cannot see it directly, a cosmic rebound, the universe pushing back. But the shock wave, traveling outward through the dense material of the star's interior, begins to weaken. About 150 kilometers from the center of the newborn neutron star, the shock wave stalls. It has lost too much energy to neutrinos cooling the region, to the photodisintegration of iron that consumes energy instead of releasing it. The shock sits there, stalled, like a wave that has crashed against an invisible barrier. You watch, waiting, wondering what will happen next on your journey. For a few hundred milliseconds, fractions of a single second that seem to stretch into minutes as you experience them, the explosion hangs in the balance. Will the shock wave revive and blow the star apart? Or will it fade, allowing the material to simply fall back onto the core, creating a black hole without any visible explosion at all? You are present for this moment of uncertainty, this cosmic tipping point. But then, salvation arrives in the form of neutrinos. Remember those ghostly particles streaming out from the core, passing through you just moments ago? Though they barely interact with matter, there are so many of them, and the material behind the shock wave is so dense that some of the neutrinos are absorbed. This absorption deposits energy into the stalled shock wave, heating the material, reviving the outward push. It is like breath returning to a dying flame, like warmth flowing back into frozen limbs. You sense the revival, the renewal of momentum. The shock wave revives. It begins to move outward again, accelerating now, pushing through the star's outer layers with growing strength. The explosion has begun in earnest. The star's outer envelope, hydrogen, helium, oxygen, carbon, all the elements created during its long life, begins to move outward, slowly at first, then faster and faster. You are here, traveling with the shock wave now, experiencing the beginning of the great expansion. The transformation you have been waiting for is underway. Your journey continues. You are traveling now with the shock wave as it races through the star's interior at thousands of kilometers per second. As it passes through each layer, through the silicon burning shell, through the oxygen burning region, through zones of carbon and helium, and finally through the thick hydrogen envelope, it heats the material to incredible temperatures. The star's insides are being stirred, mixed, heated to incandescence. You are present as the star's carefully layered structure is transformed into beautiful chaos. This mixing creates beautiful complexity in what will become the expanding debris. Heavy elements that formed deep in the core are being carried upward into layers that were once pure hydrogen. The onion-like structure is being scrambled, creating turbulent fingers of metal-rich material reaching up toward the surface, while hydrogen-rich streamers are being pulled down toward the center. It is chaos at a cosmic scale, but even chaos has its own kind of beauty, its own intricate patterns. You witness these patterns forming, swirling, dancing through the star's interior. And then, after traveling through hundreds of thousands of kilometers of stellar material, the shock wave reaches the surface. This moment is called shock breakout, and it happens astonishingly quickly. In just seconds, the shock punches through the star's visible surface and releases its energy into empty space. You are here for this moment, this birth. What you see from your peaceful vantage point is a sudden flash, not harsh or frightening, but brilliant and brief, like the first glimpse of dawn breaking over a horizon. The star, which had seemed to dim slightly during the collapse, suddenly brightens with intense ultraviolet and X-ray light. This is the shock breakout flash, lasting only seconds, announcing to the universe that a star has begun its final transformation. You are bathed in this light, safe within it, warmed by it. The flash fades quickly, but what follows is even more magnificent. The entire outer envelope of the star is now expanding outward, heated to tens of thousands of degrees by the passing shock wave. The star begins to brighten rapidly, its light climbing in intensity. Within hours that you experience fully, present for every moment, it becomes as bright as hundreds of millions of suns. Within days, it reaches its peak brightness, an absolute magnitude that would make it visible across millions of light years, outshining entire galaxies if it happened to be in the foreground of your view. You are here, witnessing this incredible brightening, this cosmic dawn. This is the supernova in full bloom, and it is glorious. From your safe distance, you watch as the star transforms from a single point of red light into a blazing beacon, brilliant white-blue in the center, with shells of red and amber light expanding outward in all directions. It is as if the star has decided to show the universe everything it was hiding inside, all its inner beauty, all its accumulated light, released in one spectacular display. And you are here to receive this gift, this revelation. The energy released in this event is almost incomprehensible. In just a few seconds, the supernova unleashes about 10 to the power of 44 joules. That's a 10 with 44 zeros after it. To put this in perspective, this is roughly equivalent to all the energy our sun will emit over its entire 10 billion year lifetime. The star is burning through billions of years of solar energy in the span of a few heartbeats. You are present for this immense release, feeling the power of it even as you remain safe and protected. The light that reaches you is gentle, beautiful, warming your spirit without threatening your being. You are here, experiencing this, but you are safe. The expanding material moves outward at tremendous speeds, 5,000 to 20,000 kilometers per second, which is roughly 3 to 10% of the speed of light. Yet, from your perspective, time seems to slow. The expansion appears graceful, almost leisurely, as shells of glowing gas drift outward like ripples on a cosmic pond. You watch each shell, each layer, as it expands past you. Each shell glows with its own color, its own temperature, blue-white at the hottest inner regions, transitioning to red and amber further out, and finally to deep crimson at the outermost edges. You are surrounded by this expanding rainbow of light, floating safely within the beauty of it. The colors wash over you, calm you, carry you deeper into this cosmic experience. Within just a few hours of the explosion, the expanding material enters what astronomers call the homologous expansion phase. This is a beautiful state where the velocity of each piece of ejected material becomes fixed, proportional to its distance from the center. The faster moving material is farther out, the slower material closer in, and this relationship remains constant as the debris expands. It is order emerging from chaos, a natural sorting of the material by speed and position. You are here, witnessing this order, this cosmic organization. And you continue to watch, breathing slowly, calmly, as the star transforms before your eyes. Your journey through the supernova continues, deeper and deeper into this experience. Days pass on your journey, and you are still here, still present, floating peacefully as the supernova reaches its peak brightness. This peak is not a sharp spike but a gentle plateau, a sustained brilliance that holds steady for weeks or even months. You have time to appreciate it, to bask in it. The expanding envelope is now optically thick, meaning light cannot easily escape through it. Photons created in the hot interior scatter countless times, bouncing from atom to atom, taking a long, meandering path before finally escaping into space where you can receive them. This creates a sustained glow, powered initially by the shockwave's energy, but then by something else, something created in the explosion itself, radioactive elements. Deep in the expanding debris, in the hottest regions where the shock wave was strongest, nuclear reactions created isotopes that are unstable, isotopes that will decay, releasing energy as they transform into more stable forms. You are here as this radioactive glow begins, as the supernova finds a new source of power. The most important of these is nickel, 56, an isotope created in abundance during the explosion. Nickel, 56, is unstable, with a half-life of just 6 days. It decays into cobalt, 56, which in turn decays with a half-life of 77 days into stable iron 56. Each decay releases gamma rays, high-energy photons that heat the expanding material from within, keeping it glowing. You feel this warmth continuing, this gentle internal fire that sustains the supernova's brilliance. This is why the supernova continues to shine long after the initial explosion, and why you can remain here, bathed in its light, for such an extended time. The radioactive decay provides a steady source of energy, like embers glowing in a fireplace hours after the flames have died down. The light curve, the graph of brightness over time, follows the decay rate of cobalt 56 remarkably closely, confirming that this radioactive heating is indeed the power source for the supernova's prolonged brilliance. You are experiencing this slow burning, this long glow. As the weeks turn into months on your journey, the expanding shell continues to grow, now spanning light days in diameter. You watch it expand around you, past you, through the space where you float. The material is cooling as it expands, and the color of the light shifts gradually from blue-white toward red and infrared. This is the natural progression of any hot object cooling, from white heat to red heat toward darkness. But this cooling takes time, measured in months and years rather than moments. You have time to witness each phase, each color shift. The ejecta, the expelled material, passes through different cooling phases as you watch. At first, when the material is hottest and densest, it emits mostly ultraviolet and blue light. As it expands and cools, the emission shifts to visible light, then to red, and eventually to infrared. The expanding shell is like a cooling ember, its color telling the story of its temperature, its glow telling the story of the radioactive decay happening within. You are here to read this story written in light and color. For a Type II supernova like this one, classified by the presence of hydrogen in its spectrum, there is a characteristic brightness plateau that lasts for months. This plateau occurs because the hydrogen in the outer envelope is recombining, with electrons returning to their atoms after being stripped away by the shock wave. This recombination releases energy at a steady rate, creating the extended plateau phase in the light curve. You experience this plateau, this long, sustained glow that holds steady as you float here in space. From your vantage point, you watch as the brilliant point of light gradually dims and reddens, like a sunset that lasts for seasons. The supernova, which briefly outshone entire galaxies, is now merely as bright as hundreds of millions of suns, then millions, then thousands. It is fading, but slowly, gracefully, giving you time to appreciate each phase of its evolution. You travel with it through this fading, this gentle decline. The expanding debris is not uniform. As you look more closely, you can see that the explosions are often asymmetric, with material moving faster in some directions than others. Polarization measurements reveal non-spherical ejecta patterns, multipolar structures, finger-like projections of dense material punching through lighter layers. This asymmetry likely comes from instabilities during the explosion, turbulent mixing, regions where the shock wave was stronger or weaker, places where dense bubbles of newly formed nickel broke through the lighter outer layers. You see these structures forming around you, complex and beautiful. These instabilities have beautiful names: Rayleigh-Taylor instabilities, where heavier material sitting atop lighter material creates finger-like structures. Vibrational instabilities in the newborn neutron star core. Macroscopic mixing reaching speeds of hundreds of kilometers per second. But what these technical terms describe is really the star's last display of complexity, its final artwork written in glowing gas and expanding shells. You are here, floating among this artwork, part of this cosmic gallery. And you, floating peacefully in space, watch this evolving masterpiece with quiet wonder. The supernova is no longer the brilliant beacon it was at peak. It has settled into a long, slow glow, a cosmic afterglow that will persist for years, then decades, then centuries. You are witnessing the transition from stellar death to something new, the birth of a remnant, the scattering of elements, the preparation of the cosmos for its next chapter. Your journey continues, deeper into time. The light reaching you from the supernova is not uniform in color. If you could spread it out into a rainbow, into a spectrum, you would see something beautiful and complex. You take a moment on your journey to truly look at this light, to read its message. In the early days after the explosion, the spectrum shows broad features, smooth continua of light that peak in the ultraviolet and blue. This is the blackbody radiation from the hot, expanding photosphere, the visible surface of the ejecta. You are receiving this primordial light from the very surface of the explosion. But soon, as the ejecta expand and cool, spectral lines begin to appear. Dark absorption lines and bright emission lines that reveal the composition of the material. Each element has its own unique fingerprint in the spectrum, a pattern of lines that marks its presence like a signature. Hydrogen creates strong lines in the red and blue parts of the spectrum. Helium shows itself through different lines. Oxygen, carbon, silicon, calcium, iron, each adds its own pattern to the symphony of light. You are learning the star's composition simply by being here, by receiving this light. The shapes of these lines tell their own story. Many of them show what astronomers call P Cygni profiles, a distinctive shape with a blue shifted absorption component and a red shifted emission component. This profile is the signature of expanding material. Atoms on the near side of the expanding shell are moving toward you, absorbing light and shifting it to bluer wavelengths. Atoms on the far side are moving away, emitting light shifted to redder wavelengths. The P Cygni profile is the calling card of an expanding atmosphere, a clear signal that material is racing outward into space, outward past you, around you. You are surrounded by this expanding shell. In the very earliest moments, just after shock breakout, moments you witnessed firsthand, the spectrum was simpler, a nearly pure blackbody continuum, a smooth curve of light emission that peaked in the ultraviolet. This was flash spectroscopy, capturing the brief moment when the shock first broke free and the star's surface was simply hot and featureless. But within hours, the flash faded, and if there was material around the star, gas that was blown off in earlier episodes of mass loss, this circumstellar material lit up when the flash hit it, adding narrow emission lines to the spectrum like bright threads woven into a tapestry. You saw this happen. You were present for this illumination. As weeks pass and the supernova enters its plateau phase, the spectrum becomes more complex. Iron lines become prominent, especially in the ultraviolet, where they create what astronomers call line blanketing. These iron lines are so numerous and so strong that they absorb a significant fraction of the ultraviolet light, redistributing it to longer wavelengths in the visible spectrum. This process shapes the observed colors and influences the peak luminosity. It is the star's composition literally determining how you perceive its brightness as you float here watching. In certain types of supernovae, like type IN, the N standing for narrow, the spectrum shows both broad and narrow emission lines. The broad lines come from the rapidly expanding ejecta, but the narrow lines come from much slower-moving circumstellar material that the star ejected before exploding. When the supernova ejecta slam into this circumstellar material, they create bright interaction zones, and the spectrum captures this collision, showing both the high-speed ejecta and the slower, pre-existing shell. You would see both, feel both, if you were present at such an event. Months after the explosion, months into your journey, the supernova enters what is called the nebular phase. The ejecta have expanded so much that they are now optically thin. Light can pass through them freely. You can see deeper now, into the heart of the remnant. The spectrum changes dramatically, dominated now by forbidden emission lines. These are spectral features that can only be produced in extremely low-density environments, where atoms have time to undergo transitions that would normally be quenched by collisions in denser gas. You are witnessing these rare transitions, present in this rarefied cosmic environment. These forbidden lines are treasure troves of information. They reveal the abundances of different elements deep in the ejecta, the zones that were once buried in the star's core. You see lines from oxygen, from calcium, from iron, all the metals created during the star's life and death. The relative strengths of these lines tell the story of the star's mass, the energy of the explosion, the mixing that occurred during the blast. The light is telling a detailed story, and you are here to receive it, to understand it on a deep, intuitive level. All of this, the colors, the lines, the shapes of spectral features, flows toward you as pure light, as information encoded in photons that have traveled through space to reach you. You, floating peacefully in your observation point, are receiving this light, this message from the transformed star, learning its story through the universal language of the spectrum. You are bathed in this knowledge, surrounded by this information. Breathe slowly and let the light wash over you. Each photon that reaches you carries a tale of fusion and collapse, of shock waves and radioactive decay, of elements forged in the heart of a dying star. The spectrum is a gift from the star to the universe, a final communication before it transforms into something new. And you are here to receive this gift, to witness this communication. Your journey continues. Part 7. The Hidden Heart. While the brilliant outer shells of the supernova expand and cool around you, something remarkable sits at the center, hidden for now beneath the glowing debris. Remember the core that collapsed at the very beginning of your journey? That dense sphere of neutrons that formed when the star's heart imploded? It is still there, and it has become something extraordinary. You sense its presence, even though you cannot yet see it. This is a protoneutron star, a newborn stellar remnant that is among the densest objects in the universe. It is only about 20 kilometers across, small enough to fit within the boundaries of a large city, yet it contains between 1 and 2 times the mass of the Sun. A sugar cube-sized piece of this material would weigh as much as a mountain. The atoms have been crushed so tightly that electrons have merged with protons to form neutrons, and these neutrons are packed together at nuclear density, touching each other the way particles touch in an atomic nucleus. You are in the presence of this incredible object, this compressed stellar heart. The protoneutron star is extraordinarily hot at first, with internal temperatures reaching hundreds of billions of degrees. But it cools rapidly, primarily by emitting neutrinos, those same ghost particles that streamed past you earlier in your journey. Over the course of minutes, these ghostly particles carry away most of the star's gravitational binding energy, the energy that was released when the core collapsed. The neutrinos stream out freely, barely interacting with matter, cooling the nascent neutron star like invisible hands drawing heat from a forge. You feel them passing through you even now, carrying away the star's birth heat. In the hours and days after the collapse, neutrino-driven winds blow material off the surface of the protoneutron star. These winds are gentle compared to the main explosion, but they are important. They carry away material enriched in lighter elements produced by rapid neutron capture, elements like europium and other rare metals that will eventually find their way into the interstellar medium, available for future generations of stars and planets. You are here as these winds flow past you, as this enriched material joins the expanding debris. The newborn neutron star may be spinning rapidly, rotating hundreds of times per second, if the original star's core had significant angular momentum. As matter collapsed inward, conservation of angular momentum caused it to spin faster, like a figure skater pulling in her arms. If the neutron star has a strong magnetic field, and many do, this rapid rotation combined with a magnetic field creates a cosmic lighthouse, a pulsar that sweeps beams of radiation across space with each rotation. You might detect these beams sweeping past you, regular as clockwork. But not every core collapse creates a neutron star. If the original star was massive enough, or if too much material falls back onto the protoneutron star after the initial explosion, the core may continue collapsing, crushing past the point where neutron degeneracy pressure can hold it up. In this case, it forms a black hole, a region of space-time so warped that not even light can escape its gravitational pull. You would feel this, sense this profound alteration of space itself if you were near enough. Black hole formation is gentler than you might imagine, in a cosmic sense. There is no additional explosion, no violent burst of energy. The core simply continues to collapse until it passes within its own event horizon, the boundary beyond which nothing can return. From the outside, as you watch, you would see the collapsing material appear to freeze at the event horizon, its light redshifting to invisibility. The black hole does not destroy matter in the sense of making it cease to exist. Rather, it sequesters it behind the event horizon, removing it from your view, from the observable universe. Some stars, perhaps 1 in 10 core collapse supernovae, fail to explode at all. These are called failed supernovae or direct collapse events. The core collapses, a brief neutrino burst escapes, which you would feel, but the shock wave never revives. Instead of a brilliant supernova, the star simply dims and disappears as all its material falls back onto the forming black hole. It is a quieter ending, less spectacular but no less profound, a star simply vanishing from view, leaving behind a hidden gravitational well. But you are fortunate. Your star exploded magnificently, and you are here to witness its full glory. In your case, in the star you have been traveling with, a neutron star has formed. And due to asymmetries in the explosion, regions where the shock wave was stronger in some directions than others, the neutron star receives what astronomers call a natal kick. Like a cue ball struck off-center, the neutron star is flung away from the explosion site at high velocity, sometimes as fast as 1,000 kilometers per second. It will wander through the galaxy for eons, a dense, rapidly spinning ember marking where a star once lived. You watch it begin this journey, this wandering path through space. Years after the explosion, years into your timeless journey, when the expanding debris has grown thin enough for radiation to penetrate, you begin to see hints of this central object. If it is a pulsar, you detect periodic flashes of radio waves, X-rays, or even optical light as the beam sweeps past you. The pulsar pours energy into the surrounding material, creating what is called a pulsar wind nebula or plerion, a bubble of high-energy particles and magnetic fields that glows with synchrotron radiation, the light produced when electrons spiral around magnetic field lines at nearly the speed of light. You are here to witness this birth, this new phase in the remnant's life. All of this lies at the center of the expanding supernova remnant where you float. It is the secret heart of the explosion, the transformed core of the star that started your entire journey. You sense its presence, feel its influence, even as you wait for the debris to clear enough to reveal the remnant's nature fully. Your journey has brought you to this understanding, this appreciation of the hidden depths. Breathe deeply. Feel the sense of mystery, of depth, that comes from knowing something profound and powerful is hidden just beyond your full view. The universe keeps some secrets, revealing them only slowly, only with patience. And you are patient, you have time, you are on a journey that unfolds at the pace it needs to. You continue to float, to wait, to witness. The expanding supernova debris around you is not just hot gas and light. It is also a treasure trove of elements, atoms that did not exist before the star formed or before it exploded. This is one of the supernova's greatest gifts to the universe, the creation and dispersal of heavy elements that will enrich the interstellar medium and become the building blocks for future generations of stars, planets, and perhaps even life. You are surrounded by this gift, floating among newly created atoms, bathed in the materials that will one day build worlds. Remember the onion-like structure of the star before it exploded, the structure you witnessed at the beginning of your journey? Each layer was burning different elements, fusing them into heavier ones. The outer layers contained hydrogen and helium, the primordial elements created in the Big Bang. Moving inward, you encountered shells rich in carbon and oxygen, then neon and magnesium, then silicon and sulfur, and finally iron at the very center. You saw all of this, experienced all of this. When the explosion occurred, the explosion you witnessed, that you were present for, all these layers were ejected into space. The material is now expanding outward around you, past you, carrying with it the entire periodic table of elements up to iron. Carbon for the building of organic molecules. Oxygen for water and for breathing. Silicon for rocks and planets. iron for planetary cores and for the hemoglobin in blood. All of these elements, forged in the nuclear furnace of the star and its dying convulsions, are now spreading through space, ready to be incorporated into new structures. You are floating among the raw materials of future worlds. But the supernova creates even heavier elements, elements beyond iron that cannot be made by normal stellar fusion. This happens through processes called neutron capture, where atomic nuclei capture free neutrons and grow heavier. In the intense conditions of the supernova explosion, conditions you experienced, that you were present within, neutrons are abundant, and they can be captured rapidly, building up very heavy, neutron-rich nuclei. You are here as this process occurs, as atoms grow heavier, more complex. This is the R process, the rapid neutron capture process. It creates elements like gold, platinum, uranium, and other rare heavy metals. The gold in any wedding ring, the platinum in catalytic converters, the uranium that fuels nuclear reactors. All of these were created in supernova explosions billions of years ago, then scattered into the interstellar medium, eventually finding their way into the dust cloud that formed our own solar system. And you are here now, present at the moment of their creation, floating among newly formed gold atoms, platinum atoms, uranium atoms. There is also a rarer process called the P process, the proton capture process. In the hottest regions of the explosion, where temperatures briefly reach billions of degrees, regions you pass through on your journey, protons can be captured by existing nuclei, creating proton-rich isotopes that are rare and valuable. Elements like titanium, 44 for instance, are produced this way, leaving radioactive traces that can be detected years after the explosion. You were there when these rare isotopes formed, present at their cosmic birth. The mixing that occurred during the explosion, those Rayleigh-Taylor instabilities and macroscopic flows you witnessed earlier, ensures that these newly created elements are distributed throughout the ejecta. Heavy metals from the core are carried upward into hydrogen-rich outer layers. The debris around you is now chemically heterogeneous, a mixture of primordial hydrogen and helium with freshly made carbon, oxygen, silicon, iron, gold, and everything in between. You float in this cosmic soup, this primordial mix. As the expanding debris cools over the months and years following the explosion, time that you experience in this timeless journey, some of the atoms begin to stick together, forming the first solid particles since the star's destruction, dust grains. These grains are tiny, submicroscopic particles of carbon, silicon dioxide, iron, and various compounds. But they are important. Dust grains act as seeds, surfaces where atoms can meet and bond, forming molecules. They absorb starlight and re-emit it as infrared radiation. They scatter light, creating beautiful nebulae. You watch these first grains form around you, condensing from the cooling gas. Observations of young supernova remnants using infrared telescopes have detected this dust formation happening in real time. Within the first few years after explosion, the cooling ejecta begin to show excess infrared emission, the signature of newly formed dust grains warming in the glow of the radioactive decay. The supernova is becoming a dust factory, creating the raw materials for planets and for the interstellar clouds where new stars will one day be born. You are present at this cosmic forge, watching creation happen. The supernova also accelerates particles to extremely high energies, creating cosmic rays. These are primarily protons and atomic nuclei, but moving at close to the speed of light, carrying enormous amounts of kinetic energy. The shock wave, as it plows through the surrounding interstellar medium, acts like a particle accelerator, using magnetic fields to bounce particles back and forth across the shock front, giving them more and more energy with each crossing. You feel these particles streaming past you, through you, accelerated to incredible speeds. These cosmic rays eventually escape the remnant and travel through the galaxy. Some of them will reach Earth, where they strike the upper atmosphere, creating showers of secondary particles that rain down to the surface. Every second, dozens of cosmic rays pass through human bodies, particles that were accelerated by supernova shocks, perhaps hundreds or thousands of years ago, now completing their journey. The particles passing through you now will one day make that same journey. This is the cosmic recycling program at its finest. Matter that was once locked in the core of a star, fused and transformed through nuclear reactions, is now spreading through the galaxy around you, ready to be incorporated into new structures. Nebulae will condense from this material. Stars will form. Planets will coalesce. And on at least one of those planets, in one corner of the galaxy, life will arise, built from the atoms created in supernovae like the one you are experiencing tonight. You are, in a very real sense, made of stardust. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stars and dispersed by supernovae. You are not separate from the cosmos. You are part of it, intimately connected to these massive stellar explosions that have been occurring for billions of years. And here, now, on this journey, you feel that connection deeply, profoundly. Take a moment to feel this connection. You are watching a star transform, watching it scatter its essence into space, and you are made of the same essence from earlier stars, earlier supernovae. The circle continues, endless and beautiful, matter transforming and reforming in an eternal cosmic dance. You are part of this dance, you have always been part of it, and you always will be. Your journey continues, deeper into understanding. Years have passed now in your journey, though time has become fluid, dreamlike. You are still here, still present, still floating peacefully in space. The supernova's brightness has faded considerably from its peak. Where once it outshone entire galaxies, it is now merely the brightness of a bright star, and it continues to dim. The radioactive decay that powered the light curve for so long, the decay of cobalt-56 into iron-56, has largely completed. The 111-day half-life has cycled through many times, and most of the cobalt has transformed into stable iron. The glow is gentler now, softer, like twilight settling over a vast landscape. The expanding debris now spans several light years in diameter, and it is still growing around you, through the space where you float. The material continues to move outward at thousands of kilometers per second, and it will keep moving for millennia, until it has expanded so much that it merges with the general interstellar medium, becoming indistinguishable from the background gas and dust between the stars. But for now, you are still here, still witnessing, still present within the expanding remnant. The ejecta are now in the nebular phase, optically thin and glowing primarily from forbidden emission lines. The expanding shell has cooled to temperatures where atoms can retain their electrons, and the light comes not from thermal radiation but from specific atomic transitions, particularly in oxygen, calcium, and iron. These forbidden lines produce a beautiful glow that you can see around you, often with distinct colors: red from singly ionized oxygen, green from doubly ionized oxygen, blue from sulfur and other elements. You are bathed in these colors, surrounded by this gentle, multi-hued glow. If you could see the remnant with eyes sensitive to different wavelengths, and perhaps, on this journey, you would witness a magnificent structure. In optical light, you would see glowing filaments and shells, tendrils of gas marking where the shock wave compressed and heated the original ejecta and the surrounding material. In X-rays, you would see the hottest regions, zones where the shock is still moving through dense material, heating it to millions of degrees. In radio waves, you would detect synchrotron radiation from relativistic electrons spiraling in magnetic fields, marking the positions of the shock fronts and any pulsar wind nebula at the center. You see all of this now, all the wavelengths at once, a complete picture of the remnant's beauty. Decades after the explosion, decades into your timeless journey, something beautiful occurs that you are here to witness. Light echoes. These are not echoes of sound, but of light itself. The brilliant flash of the supernova traveled outward at the speed of light, and there are dust clouds nearby, dense regions of interstellar dust lying off to the sides of your line of sight to the supernova. The light from the explosion can reflect off these dust clouds and reach you years or even centuries after the event, having taken a longer path. When this happens, you see expanding rings or arcs of light around the position of the supernova. These are not new explosions. They are reflections, light that took a longer path to reach you because it bounced off dust along the way. The light echoes can reveal structures in the surrounding interstellar medium, showing where dust clouds lie that were previously invisible. They are like cosmic archaeology, revealing the environment around the supernova that was hidden before the explosion. You watch these echoes appear, these ghosts of the original flash. The expanding remnant reveals more asymmetries as you watch. As the debris spreads and thins, you can begin to see detailed structures, bullets of fast-moving material, cavities blown by early winds from the progenitor star, dense equatorial tori if the star was spinning rapidly before it exploded. Each supernova remnant is unique, shaped by the particular properties of the star that exploded and the environment into which it exploded. This one is unique too, and you have been present for its entire unfolding. Centuries after the explosion, centuries that pass like moments in your experience, the supernova remnant enters its final evolutionary phases. The expanding ejecta sweep up the surrounding interstellar medium, creating a shell of shocked gas that glows primarily from collisional heating rather than from the supernova's own energy. This is the beginning of the remnant's merger with the general interstellar medium. Eventually, the expansion will slow, the shell will break apart, and the material will disperse completely, mixing thoroughly with the gas and dust between the stars. You are here to witness this gradual dispersal, this gentle dissolution. The elements created in the explosion, all that carbon, oxygen, silicon, iron, gold that you saw being formed, will now be available for incorporation into new structures. The next generation of stars that forms in this region of the galaxy will be slightly enriched in heavy elements compared to earlier generations. Planets that form around these stars will have more rocky material, more metals, more of the ingredients needed for complex chemistry and perhaps for life. The gift continues, spreading through the galaxy, and at the center of the remnant, the neutron star, if that is what formed, continues its silent vigil. It may have slowed its rotation over the centuries as it lost energy to radiation, but it is still there, a dense, compact memorial to the star that once was. Or perhaps a black hole sits at the center, invisible but marked by the orbits of nearby material, a gravitational well that will persist for as long as the universe exists. Either way, you sense its presence, feel its quiet existence at the heart of the expanding shell. From your vantage point, the supernova has transformed before your eyes, around you, through your experience. It has gone from a brilliant beacon to a fading glow to a subtle nebula, and now to something almost invisible, merging with the background. But it has not disappeared. Its matter persists, its energy persists, its influence on the galaxy persists. The supernova has become part of the cosmic ecosystem, its material recycled, its legacy continuing in every atom of heavy elements it created and dispersed. You have been here for all of it. You have witnessed the complete life cycle of a massive star, from its stable, shining existence through its dramatic transformation to its quiet dispersal into the interstellar medium. It was a journey measured in millions of years of life, seconds of collapse, months of brilliant display, and centuries of fading. And through it all, you have been present, floating safely, peacefully, observing, experiencing, being part of this cosmic transformation. Your journey is nearly complete now. The supernova has faded now to near invisibility, its light dwindled to a whisper, its expanding shells so thin and distant that they are barely distinguishable from the background glow of the galaxy. The transformation is complete. What was once a single massive star is now scattered across light years of space, a slowly expanding cloud of enriched material that will eventually become part of new stars, new planets, perhaps even new life. And you have been here, present, for this entire transformation. You, floating in your comfortable vantage point, have traveled through this entire journey. You have experienced the star in its prime, glowing steadily with the energy of fusion. You have been present as it ran out of fuel, as its core collapsed, as the shock wave revived and tore the star apart. You have witnessed the brilliant peak, the long plateau, the slow fade into darkness. You have learned about the elements created, the remnant left behind, the cosmic cycle of matter that continues forever in the universe. You were there. You experienced it all. And now, as the supernova's light fades to almost nothing, as the debris spreads and cools and merges with the interstellar medium, your journey too can come to rest. The show is over. The transformation is complete. The universe has done its work, and it will continue to do its work long after you have drifted into sleep. But you were here. You witnessed it. You were part of it. Take a deep breath and release it slowly. Feel the tension leaving your body, the thoughts quieting in your mind. You are small compared to the cosmos, small but not insignificant. You are made of the same atoms created in supernovae like the one you just experienced. You are connected to this process, part of this eternal cycle of matter and energy. You have always been part of it, and you always will be. The space around you is quiet now. The brilliant beacon has faded. The expanding shells are too faint to see without sensitive instruments. Only the stars remain, distant points of light scattered across the darkness, each one following its own path, burning its own fuel, living its own span of years or millions of years before its own transformation comes. You are among them, between them, part of the cosmic tapestry. You are floating, drifting, peacefully suspended in the gentle darkness. There is no cold, no fear, no urgency. Only the quiet stillness of space, the soft glow of distant stars, and the slow rhythm of your own breathing. You are here, but you are also letting go, releasing your hold on consciousness, preparing to drift into rest. The supernova's light continues its journey outward, moving away from the explosion site at the speed of light, carrying news of the transformation to ever more distant corners of the universe. But you need not follow it. You have seen what you needed to see. You have experienced what you needed to experience. Now you can rest. Your journey is complete. Let your attention drift away from the distant remnant. Let your thoughts grow quiet. You are safe here, floating in the cosmic darkness, wrapped in warmth and peace. The universe will continue its work without your observation. Stars will live and die. Elements will be created and dispersed. New worlds will form. The cycle will continue, as it always has, as it always will. And you are part of it, always have been, always will be. And you are free to drift into sleep, into rest, into the quiet darkness that is not empty but full of potential, full of peace, full of the gentle rhythms of the cosmos unfolding all around you. Your journey has brought you here, to this place of rest, and now you can simply let go. The stars are shining softly in the distance. The supernova remnant expands silently, invisibly, fulfilling its role in the cosmic cycle. And you float here, breathing slowly, feeling smaller and smaller, more and more at peace, more and more ready to release your hold on consciousness and slip into the warm embrace of sleep. You have traveled far, experienced much, and now it is time to rest. There is nothing you need to do, nothing you need to achieve, nothing you need to understand. The universe will take care of itself. The stars will burn. The supernovae will explode. The elements will scatter and reform. And you can simply rest. Your journey is complete. You have witnessed the transformation. You were there. And now you can sleep. Let go. Let yourself drift. Feel the soft darkness enfolding you like a blanket. Feel your breathing becoming slower, deeper, more rhythmic. Feel your thoughts becoming quieter, softer, more distant. You are safe. You are at peace. You are connected to the cosmos and to the endless cycle of transformation. You have been on a journey, and now the journey has brought you home. The supernova has taught you something profound, though you may not consciously remember what it is. It has shown you that endings are also beginnings, that death feeds life, that scattering is also sowing, that transformation is natural, beautiful, and ongoing. You were there to learn this, to feel this, and now you carry it with you into sleep. And now, as you drift deeper into rest, as your consciousness fades like the supernova's light, you can carry this knowledge with you into sleep. You can rest in the understanding that you are part of something vast, something ancient, something that will continue long after your individual consciousness has released its grip on the waking world. You were there. You experienced it. And now you rest. Breathe in and breathe out, slowly, gently, peacefully. Feel yourself becoming lighter, floating higher, drifting away from the need to observe, to understand, to stay awake. You have seen enough. You have experienced enough. Now is the time to rest. Your journey is complete. The darkness is not empty. It is full of stars, full of matter, full of energy in its endless forms. And you are part of this fullness. You belong here. You are safe here. You can rest here. You have always belonged here, in this cosmic dance, in this eternal cycle. Let the last traces of the supernova's light fade from your awareness. Let the stars become dim and distant. Let the vast spaces between them expand in your mind until they fill everything, until there is nothing but gentle, peaceful, comfortable darkness. You are in this darkness, part of this darkness, safe in this darkness. And in this darkness, you can sleep, deeply, peacefully, safely, knowing that the universe continues its work, that the cycle continues, that everything is as it should be. You were there. You witnessed. You experienced. And now you rest. Good night, traveler. Good night, witness. Good night, child of stardust. The supernova's transformation is complete, and so is your journey tonight. Rest now. Dream gently. And when you wake, you will carry with you the memory of having been there, of having witnessed something profound, the death and rebirth of a star, the continuation of the cosmic cycle, the beautiful, eternal unfolding of the universe. You were there, and now you sleep. Sleep well. The stars are watching over you, and you are home.